Okay, so don't worry about taking notes or necessarily like trying to keep up. You know, do pay attention to what I'm saying, but I know the video for the material covered previously is still uploading. So unless you've read the book, you're not going to be probably on this section. So just, you know, go with the flow. Don't worry about taking notes. You can always come back and watch it again. It's probably going to be pretty short. Realistically, we don't have that long. So here we go. So I'm going to skip ahead to 4.4, and we're going to look at the graphs of logarithmic functions. So something I want to get out there, logs are the inverses of exponentials, which is what we have been going over. So when you have an exponential graph, you'll notice that it will always pass the horizontal line test. So what this means is that it's 1-to-1. And it also means, because it's 1-to-1, that it has an inverse. And since it's really difficult to solve something like this, like if I gave you 10 to the x equals 43, obviously, you know, you could take the xth root of both sides, but then you would just be left with 10x 43, which that's not any better in my opinion, and we still can't solve it using basic algebra. So when we have an inverse, that would allow us to, in a way, make this solvable. So if you have an inverse of, if you have a function of b to the y equals x, and ignore the fact that, you know, the x and the y are switched. So we're just going to say this is our function. Then your inverse would be log base b x equals y. So they are inverses of each other, and this will help us solve things. So looking at it graphically, so if you could, of course, you see an exponential. Now the inverse is usually along some center line. So as you could imagine, the log will look something like this. So do you see how we go forward in time and these values for our exponential just get huge, right? Well, we've sort of counteracted that by applying an inverse, which is why I'm sure some of you from maybe chemistry, when you do, I think, titration, you will notice that you have to apply the log to all of your data. This is why, because it makes it on a much more manageable scale like pH, where it takes large differences and compresses them into smaller differences. So notice it for the inverse here, as we go forward in time, these differences, they're not that bad. Whereas for an exponential, the differences, you know, you can see are huge. So this is what the graph of a logarithm will look like. So it will look like an upside down exponential. A lot of things are modeled this way. So one of the benefits of having them be inverses is that you know that the domain and the range of your exponential are going to be your range and your domain of your logarithmic function. So notice the domain of the exponential is
Did she just freeze for you guys?
okay. Sorry about that. Teams just absolutely freaked out. I am still sharing my screen. Oh, something's wrong with my network. I apologize if I cut in and out. But I'm literally like, what the heck spectrum? I'm literally sitting right next to the router. Like, I'm there. We're best friends right now. So I'm going to have to, yeah, my apologies. Notice that the range of the exponential is going to be the domain of our log, and that can be observed right here. So notice that your log does not accept any x values greater than 0. I'm sorry, less than 0. You can't accept negative x values into your log. So, for example, log of b of, I know, -4, you can't do that. That's what I mean, it won't take values. So your parent function now, we're talking about graphs in this section. So we can compress it, we can stretch it, we can move it up and we can move it down, we can move it side to side. We can move it just like we can move any other graph. So like here, notice when we consider this function. So this is for any values of x where this inside guy has got to be greater than 0. And you can see the argument here. It cannot equal 0 or else, you would get an answer all that is not, yeah. I don't even think your calculator would give you an answer now that I think about it. So it cannot equal 0. So it's got to be strictly greater than 0. So you would solve for this inequality. And notice that that now changes the domain to all of the x values that allow it to be greater than 0. So here, we've took the inside portion. We have started solving for when it is greater than 0 because it has got to be greater than 0, which gave us greater than -3. So here's an interesting one. Log of 5 x minus 2 plus 1 is going to be equal to f of x. Ooh, where'd we go? There we go. So one thing I'm going to do to find my domain is I can just completely ignore that one. That's because this log to the base 5, x minus 2, is going to be a number in itself. Oh man. My hand. Okay, so we're going to need x minus 2 greater than 0. So I can move this 2 over by adding it to both sides, which this gives me x has to be greater than 2. So my domain is now 2 to infinity. My domain. Now, remember there are some rules of dealing with these, and since these aren't usually dealt, like equalities aren't dealt with in everyday life, there are some students that you forget, quite honestly. I know a lot of adults that still forget. So it's cool, we're good. I'm gonna remind you right here. So when you multiply or divide by a negative number, you switch the signs. You switch from this to this, or from this to this. So if I had negative 3x greater than 4, and I divide by negative 3, I would take x is less than negative 4 over 3. And the same would happen if I had to multiply by negative 3 on both sides. I would just switch it. Okay, so again, here, this is defined when the input is positive. So now they're going to set up this equality. And notice, this was what I was just talking about, where it switched the signs. So now that means our x values are going to stretch into, think of it like negative time, you know, the negative x values, which negative time, that's ridiculous, but that's sort of what we're looking at, that negative portion. So here, it would be x minus 5 is greater than 0, where x is greater than 5. Why on earth did they give us this one? Because we did not have to really switch anything. That's really weird, so I'll modify this a bit. So if it was negative x negative 5 greater than 0, we would add 5 to both sides. We would divide by negative 1, switching it over. So it would have to go from negative infinity to negative 5, non-inclusive. We don't include that. So graphing logarithmic functions. Of course, you can always make a table. That's a majority of what this book does anyways, is making table after table. But what I'm interested in is showing you that they are the inverse graphically. Notice that they are a reflection about this center line, y equals x. So they're reflections of each other across the origin. There are some things to notice. So there's a y-intercept. Everybody knows the base has a y-intercept at 0, 1. So therefore, our log will have an intercept at 1, 0. So this is bx, this is log by. Now the range becomes infinite because that was the domain of our base, and the domain will now be restricted because the range of that inverse was restricted. So these are characteristics of the function. These would be important to know. This is just like a little table. When you guys rewatch this, you can copy this down if you'd like. The main points to keep are where they happen to intersect, these points, 1, 0 and B1, and B1 and 1, 0. So notice it's going to decrease when our base is a fraction, and it's going to increase when our base is greater than 1. When our base is 1, we just get the constant function, which is a horizontal line, which does not pass the horizontal line test. So it's not 1-to-1. There is no inverse. It's not even an exponential. It's just 1. Okay. So 5 points in graphing these. Okay, I think we are, yeah, we're still recording. 5 points in graphing these. You are going to label the vertical asymptote, x equals 0. And remember, vertical asymptotes go up and down. So let's have a look up here what we mean. Notice how they don't really. All right. Oh, sorry. My network keeps losing signal and it keeps putting me temporarily on hold. Let's get back to it. Notice that you do have that asymptote, so you cannot cross that x-axis. So right here, traditionally, if you shift it over, you most certainly can. But if we're just talking about parent functions, you cannot. So we're going to draw and label the vertical asymptote is the first thing we're going to do. Then we're going to plot the intercepts 1, 0, and then the key point B1. You will draw a smooth curve through those points. You will state the domain, the range, and the vertical asymptote. So for here, log 5x. So the first thing we're going to do is, of course, we understand that we've got a vertical asymptote here. And then for number 2, we're going to plot the point 1, 0, which will be right here. And then we are going to plot the point B1. Now, what is B? B here is 5. So we will plot the point 5, 1. So that's 1. I'm going to say 5 is probably all the way out here. 5, 1. Now it wants us to draw a smooth curve. There we go. So now we will state the domain and the range and the vertical asymptote. You know, of course, the vertical asymptote is x equals 0. The domain, it'll go from 0 to infinity. The range will go from negative infinity to infinity. So those are all my y values that can exist. And here it is. Looks like we did pretty good. So here we would state the domain, the range, and an asymptote. So if we wanted to see what it would look like with a fraction for a base, this should be decreasing. Let me go up here and show you. Here we go. Notice that when your b is between 0 and 1, it goes the opposite way, so it will be decreasing. So we're going to, that asymptote is here. So I'm going to say the vertical asymptote is x equals 0. I know that because nothing is moved over or around or stretched or compressed, I know that my domain is just going to equal 0 to infinity because that's the range of an exponential. And my range is going to be negative infinity to infinity because that is the domain of the exponential. So my key points are going to be 0, 1, or I'm sorry, 1, 0. And then I will have b, comma 1. So that's 1/5, 1. So 1/5, 1. So we're going to say 1/5, 1. And it would look something, I'm sure, like this. So transformations. So notice that if we're going to move things left or right, side to side, we have got to work inside the parentheses. Everybody notice that? And notice that it will be the opposite of what you think. So the opposite of what it looks like. So if you're adding c, that's actually going to look like you're going in the negative direction. And if you're subtracting c, that's actually going to look like you're going in the positive direction. And this is along the x-axis. So that will change the asymptote to c. And remember that if you add c in parentheses, your asymptote will become the negative c. And if you subtract c in the parentheses, your asymptote will become the positive version of c. Your domain and range, the domains will change. Notice the ranges remain the same. So the domains become c to infinity. And you can see that because of the asymptotes here. It'll have to be from c to one direction. Okay, horizontal shifts of the parent function. This pretty much summarizes what was gone over above. This how-to explains what is going on. So the first thing you're going to do if you were to graph something just of this form is you're going to identify the shift. So you're going to identify C. Next, you're going to draw the asymptote. You're going to identify 3 key points. You're going to find new coordinates by subtracting it from the x-coordinate. You're going to label the 3 points, and then you're going to state the domain, the range, and the vertical asymptote. So we'll look at one that they've already solved. So here we have x minus 2. So remember, it's minus. So that means our c is going to be positive. So our c is going to be 2. Okay. C is going to be 2. We're looking at this guy. So our asymptote is going to be x equals 2. Our new domain is going to be 2 to infinity. Our range is still going to be negative infinity to infinity. So the key points. So it wants us to consider key points from the parent function. So those are going to be the points. This is from the parent function, which is just base 3. So those key points are going to be 1, 0, and then b, comma 1, so 3, 1. And then another one that they would like to consider is when it's negative 1, which is just going to be 1 over b. So now in the new function, according to what have we done? We have identified the shift. Let's go ahead and draw the vertical asymptote at x equals 2. There we go. The asymptote at x equals 2. So we've identified the 3 key points right here from the parent function. We have to find the new points by subtracting c from the x-coordinate. So what we're going to do is since we're not subtracting here because it wasn't a plus c, it was the -2, so our c is positive, we're going to actually add 2 just to the x coordinate. So that's going to be 3, 0, 5, 1, and I mean, you know, it can be worked out. So those are our points, and we would graph those. So we're going to have 3, 0. So 3 will be right here if this is 2. We're going to have 5, 1. And we're going to have 7/3. That is 2 1/3. So 2 1/3. Right over here on the other side of 3, it's going to be -1. And that will help us determine which direction. There we go. So now I'm going to, I already stated the domain and the range, so we're okay. And there's our graph. Looks great. We did a good job. Okay. I can let you guys practice with this one. So now we're going to be working outside of the parentheses. Which means that it's going to be moved up and down. And notice it gives you key points here. And it goes with the sign. So when it's plus d, it'll move up. When it's minus d, it will move down. This is just like all of the other ones. We're just shifting it on that y. So it's just going to go up and down, up and down, up and down, depending on what we're adding or subtracting. So this is similar. Some key differences are the vertical asymptote will stay the same. Notice that the domain, the range, these will all stay the same. So we're not going to be doing anything to them. The only thing we will be changing are the y coordinates by adding d to them. So this one's relatively easy. So you would, you could graph log base 3x and subtract 2. As you can imagine, that's going to go down 2. Now, if you have this one, notice it's plus 2, so we'll go up 2. So these ones are simple because they're just on the outside. So I'm going to kind of just avoid graphing them. The compressions and the stretches. These are ones I'm probably won't have you graph these by hand, so I'm just going to get that out on the table there. I just kind of want you to understand this concept. So notice that if you multiply your log by a number greater than 1, you will see your log start to rise up. So it will start being repelled by the x-axis. It's just like, ooh, get away from me. And it just will increase that distance. Notice that when you multiply it by a small number, it still has to be positive. So we're talking about a fraction. It's going to want to cling to that x-axis. It's going to want to get real close because it really likes that x-axis. So here you can see that the distance is being closed. So remember, if it's a big multiplication of log, it's going to get much further away from x, so it's going to look like the function itself is getting bigger. If it's being multiplied by a really small number, then it will get just smushed closer to that x-axis. Notice that the domain and the range and the intercepts would stay the same. We're not changing where it is located. Okay, here is an example. Notice they multiplied it by 2, which is a bigger number, so it's going to be repelled. So it's going to go up above the original function. It's going to be larger than the parent function. Here they multiplied it by half. So if we're looking at this graph here, I'm going to guess that it would be underneath here somewhere. And we'll call that y equals half log 4x. So you can do these like we always do, and you just, start on the inside the parentheses. Reflections. So reflections about the x-axis occur when you make the entire log negative. So when you make it negative, it's just going to roll over like a dog, just right over onto its back on the x-axis. If you make the x values negative, if you make all of the input values negative, then it's going to swivel side to side. Like, you heard your friend say something, so you turn immediately. And that will go right across the y. Notice this one's negative here, and notice this negative is applied on the outside. Here is the inside negative again. Oh, where did we go? There we are. So notice that the range will stay the same, the x-intercepts will stay the same, and the asymptotes will stay the same. So these will stay the same. The x-intercepts will stay the same. And this is just when we flip it. The range remains the same for both of them. The domain only remains the same if you flip it over the x, because we're not really messing with our x values, we're just messing with our y values. Do notice that when you flip it over the x, you have a change in one of the key points. And notice that when you flip it over the y, you actually have two changes. You have a change in a key point and a change in the domain. Okay. So there are two different procedures for graphing these. Again, I'm just slightly more concerned that you understand the concept than how to graph them, because there will always, like, let's face it, at this point in time, there's always going to be some program available to you to be able to graph it. And if the world does go, belly up disaster apocalypse, if you're looking for food, the least thing you're going to be concerned about is graphing a logarithmic function. So I'm not going to require you to do this by hand. Now, there may be a graphing activity that we do, but it wouldn't be by hand. So just understand the basic concepts. That all of the normal transformations still apply in the case of logarithms. So this is a reflection. Notice that everything was just reflected. So all of our x values, since it was moved across the y, all of our x values are now negative. Did not change our y values at all. Okay. So you can actually do these in your calculator. You can do logs in your calculator. And that's probably what most of this work is going to be. The test will be largely conceptual. So I'll try to come up with some questions that relate to the exam. So this is a summary. All of our transformations. Everything that we could possibly do to this. is here. And it is explained once again, if you don't like tables, it's explained sort of paragraph style. Okay, so finding the vertical asymptote of the logarithmic graph. Man, that's a big one. Well, what I can tell you is that I know my C is related to my vertical asymptote. And the only thing that's going to change my vertical asymptote is when I go side to side. And I only go side to side if something is being changed about the X on the inside of my parentheses. So if I didn't have that 4 there, the asymptote, the vertical asymptote would just be X equals 0. But since I do have something there, I know that the form is usually X minus C. So the fact that it's plus here, it means that my C is -4. So that makes my vertical asymptote -4, like right here. And let's look at this one right here. So notice that it's negative on the inside, which is the way it is supposed to be. So I can say that my C is 1. So my asymptote has to equal 1. Let's see, from a graph. What page is this? Okay. So from the graph, you can see here that we will have an asymptote at X equals -2. So that means my C equals -2. So I am going to have some part of it will be log. I don't know quite what my base will be yet, but it should at least be X plus 2. And then something or other added to the end. Okay, so notice that it was, I mean, I don't really think it was flipped, but they say it is. These can be confusing because depending on the transformation, they can look the same. So just understand to find that asymptote. All right. Here, I would know that the vertical asymptote is X equals -3. So my C would be -3. So I would have, just generally, I don't know what the other things are. You would have X plus 3 plus D. And we can go from there. Okay. Oh, that looks like that is it for this chapter. So I will actually go up here and I will expand on finding the equation from the graph because it looks like I still have about 10 minutes. So, and notice it has a vertical asymptote at X equals -2. It says it has been vertically reflected. We don't know the shifts yet, but we do know that it will have this general form. -a log x plus 2 plus k. So this would be a standard logarithmic. So it does look like it was flipped across the x. And remember, when we flip across the x, we actually do make it a negative, so it will be something negative. So it looks like it passes through the points. What points they want us to use? They want us to use -1, 1. So we just picked an approximation. To -1. picked another approximation. So now we're going to put these two things into here. So we will have, let me see, y is going to equal 1. So it's going to be negative a log, our x is negative 1. Negative 1 plus 2 plus k is going to be 1 equals negative a log 1 plus k. So remember, this is something to remember. Log of 1 equals 0. And that's, do you remember from the graph, we had the 0.10? That's what that means. So we've got 1 equals k. And then next, using the 0.21 to negative 1, we're going to have negative 1 equals negative a log 2 plus 2 plus k. So we will have negative 1 equals negative a log 4 plus k. Okay, so here we know that k equals 1, so I'm going to go ahead and plug that in. So we're going to get negative 1 equals negative a log 4 plus 1. I am going to now solve for a. So I subtract 1 from both sides, giving me negative 2 equals negative a log 4. I am going to divide by negative log 4. And that allows me to cancel out the log and get rid of the negative, so I get a. And a is going to become, these two negatives turn into positives. And that's because the negative divided by negative is a positive. Divided by log 4. So now I can write the equation as f of x equals negative 2 log 4 log, where's the original? Log x plus 2 plus 1. And we're just going to take it to assume a base 10, so a common logarithm. And that is how they got this. So one general theme you'll see in logarithms and exponentials is systems of equations. Also is something, if you haven't done it in a while, maybe you should brush up on it. So this concludes 4.4 logarithmic graphs. They have videos and I think extra practice problems at the end of every chapter. They have links to things, so it's also a good resource. It's in your textbook. Let me, there we go. Let me stop the recording. Where is, there it is.